This is part 5 in this series of videos in which I'm looking at these cheap electronics kits. You'll notice I've changed the title of the video. Got a bit tired of the comments I was getting about the spelling of the video titles. I did explain the purpose behind that in the video, but people do insist on leaving comments without watching the videos. So hence from this point forward I will be calling these cheap electronic kits. But they are mostly from China. I buy them, generally speaking, off eBay, Amazon, that sort of thing. And it's really to look at the kit from the value for money perspective. I'm not doing in-depth reviews for these, and it's really, as I say, just to see if they are fun to build and whether they're worth spending money on, if they're any good for beginners to learn with, and if they're fun to sort of play with and assemble. So we'll have a look to see what this one is. And as the instructions say, this is a function generator kit. And as I haven't really looked at this yet, it's based around an XR2206 function generator IC. So that's not a surprise. There are a number of kind of monolithic single chip solutions these days for function generators. It has been for quite a long time. In fact, about 25 years ago I built a version of a function generator. Had a nice LCD display, all the usual bells and whistles. I was trying to get out at some point and do a video on it, but this is obviously a much simpler device. And looking at the schematic in the instructions, I very much suspect this is taken directly out of the spec sheet as one of the examples. In fact, what I'll do, I'll go and try and find a spec sheet for this device, and we'll compare that to see if there's something similar to this in it. Okay, so I've got a copy of the spec sheet, or at least some of the pages out of it, and it's quite a nice sounding device. Supports sweep generation, AM, FM modulation, and can be used in all manner of circuits, of course, everything from simple function generators, which is what we have here, through to complex phase lock loops for voltage controlled oscillators, that sort of thing. Works from 0.1 hertz ish up to around a megahertz, so it's not particularly fast, but it does have fairly impressive low distortion figures, or at least that's what's quoted on this. One thing I did find while I was looking for the spec sheet is there are a number of YouTube videos on this kit, and so a few in particular are about counterfeit versions of this device, the XR2206, and also how to modify this particular kit to get more out of it. Now, I'm not going to go into that. I'm going to look at the kit as it's supplied. We will look at the output from it to see how good it is, but it might be a good learning tool if you do want to look into how to improve it, how to get the distortion lower. And one thing I have noticed on here is there's nothing connected to the symmetry pins on the device, so there is no way to finely adjust the sine wave waveform shape on this board, but you could add that if you wanted to. And sure enough, as we thought, if we look at the spec sheet, we'll see that the schematic on here is taken almost intact directly out of the spec sheet. So it's not surprising, it's not necessarily a bad thing. The other thing I would say is that the spec sheets don't really show optimized use for these devices, and in theory you should be optimizing the schematic to suit your particular purpose rather than just duplicating it. Now, this has been expanded a little bit to give a few ranges of operation, but really it's just an exact copy of the example schematic shown in the datasheet. Okay, so without further ado, we'll see what else is in the kit. and look at assembling it. Now, a quick look at the board. Quite a nice looking board. Again, the usual problem, the holes are too big. I can see that already. The holes are pretty much all the same size, and most of them are too big for the size of pins that will be on these components. And that's a common issue with these cheap boards. It makes soldering a bit more difficult, but this is actually quite a nice quality board. It's better than most of these cheap kits. And so what else we've got in the bag? It does come with a case, so we'll look at that later on. And in the bag of parts, okay, so what we'd expect, a variety of components, and I paid £4.50 for this delivered, so you probably couldn't buy the parts separately for that. And so we'll look at getting these assembled. I won't bore you showing me inserting all these components. Unlike a lot of these kits, the board does not show the value for the component. They've gone kind of down the more professional way of doing things, and there is a cross-reference to each component in the instructions, and it does tell you what each one should be, and the instructions are in English, so that's quite nice. And reading through them, it's quite good English as well, so it's not the usual collection of English words put together to make what should be sentences. The sentences do actually seem to make a lot of sense. So okay, I'll start by fitting the resistors. We'll have a quick look at it, and then we'll go through and fit all the rest of the components. Okay, that's the resistors fitted. They all went in quite nicely. As I said, the holes are too big, so it takes more solder than it should. If you are designing your own boards, then the hole sizes are actually quite important for component mounting. It not only minimises the amount of solder required, but it gives a better joint if you don't have a huge amount of solder in a very large hole. And so most big manufacturers will actually give PCB hole size recommendations for their components, and it is well worth trying to adhere to that if you can. Generally speaking, what you need to do is try to minimize the number of different hole sizes on a board design, but trying to get decent size holes for most of the components does not necessarily mean having hundreds of different hole sizes. Most manufacturers do tend to stick to fairly well defined sizes, such as 0.8 millimeters, something like that is a fairly common size, and it does make assembling the board much easier, and you end up with better results. Okay, I'll get the rest of the discrete components fitted, and we'll go from there. Okay, so that's all the capacitors fitted. Again, they went in nicely, but as I said, holes are way too big, so it does make soldering it more difficult than it needs to be, but it goes together fairly easily. Next thing I'll fit are the pin headers and the IC sockets. I'll get those fitted, and then we'll go from there. Okay, so that's the IC socket and the pin headers fitted. The next thing I need to do is fit the power socket, the in-out connector, and the pots. So I'll get these fitted, and then once we've done that, we can plug in the IC and see if it actually works. Okay, so that's the pots and connectors fitted. Next thing we can do is plug in the IC. And fit the knobs. Okay, and the jumpers allow us to select various ranges, etc. Before we do this, we'll have a quick look at the case, and I won't fit it into the case just yet, but we'll have a look at it anyway, just to see what it consists of, and then we'll try and power this up and see if it actually works. Okay, the case seems to consist of what I'm assuming are some laser cut pieces of plastic, and it's quite nice. They seem to have gone to the trouble. Okay, they're backwards, I'm assuming it's that way up. I'll take these covers off in a minute. And they've gone to the trouble of etching some text onto the cover, so presumably that's going to tell us what each of the jumpers does when we have the unit assembled. Save us having to keep looking back at the instruction sheet. So I'll just get the covers peeled off this. I won't do it on camera, they tend to be quite tedious getting these peeled off, and then we'll see how this all fits together. Okay, so that's all the backing peeled off the various parts, and what we can do now, I'm not going to assemble the case just at the moment, I'll come back and do that later. But these just all slot together, and then there are some bolts to hold everything together. So I'll do that later on, but I want to see if it actually works first. So I'll get a scope onto the bench, and then we'll see how it actually performs. Okay, I've got the board hooked up to a scope and to a power supply, and we'll see if it actually works. This is not going to be a full review, this is just really to see what sort of output it gives us. I've got the two outputs hooked up to the two channels on the scope, so the yellow trace is the square wave output, and the purple trace is either sine wave or triangle wave, depending on the position of this top jumper. I've got all the pots set to their minimum value, and I've got the frequency range jumper set to the 0.1 to 10 Hertz range, which is what's etched on the front panel of the case. Now I suspect, looking at the value of the pots, that we may have some issues, because it seems that these values will take the device outside of its normal operating range, so it'll be interesting to see exactly what it does. But what we'll do to start with is power up the board. I've got it powered from 12 volts, and we'll wait for the scope to do a full acquisition, which it has done, and as we can see there is some fairly severe clipping. Now the square wave will just be a constant amplitude square wave. Both channels of course are showing the same frequency. There's only one frequency setting for this device on this board, and the yellow channel is set to 5 volts per division, and the purple trace at the moment is set to 2 volts per division. And this is kind of strange that it's giving us such a big amplitude. The amplitude is about 7.7 volts for the sine wave and just over 11 volts for the square wave. But I've got the amplitude pot turned all the way down, so I've got a feeling they may have wired that one in backwards. We'll just try turning it up, and sure enough the amplitude has gone down. Let's need to try something else before we go any further. Okay, I wasn't quite sure if maybe the pot should have been on the other side of the board, but no, because when I turn the frequency pot up, the frequency does go up, so it looks like they've just got the amplitude pot wired in backwards. If you wanted to, of course, you could just reverse the outer two connections to the pot, and it would then work the right way round, but I'm not too concerned about that, so I think I'll leave it as it is. Next thing we want to do is test the frequency control range. So we've got two controls, one's labelled fine, one's labelled coarse. So we'll turn the fine all the way up. We'll wait for the scope to do an acquisition. It's fairly slow because it's such a low time-based setting we've got. And that's taken us up to about 0.77 Hertz, so there's not much difference. We'll turn the coarse all the way up. Wait for a full acquisition again, and that's now showing 1.63 Hertz, a bit short of the 10 Hertz that it's supposed to. We'll turn the fine back up and see what the maximum is, and that's quite interesting. Let's just check there. So yep, that is, middle one's supposed to be fine. Okay, so the action of the fine pot depends on the position of the coarse pot. If we turn the coarse down a little bit. Okay, so we'll try the next range. According to the front panel, that should be 10 Hz to 100 Hz. I'll just move the jumper. And we'll turn the frequency pots all the way down again, and that's taken us from 7.4 Hz. So I won't turn the coarse all the way out because that makes it behave in a bit of an odd fashion. In fact, we will try it and see if it does the same thing, which it does. So with fine all the way up and the coarse at about 90%, we're up at 55 Hz. So the operation of the two pots is kind of interchangeable depending on exactly where they are, but with them both all the way up, it does go up to over 200 Hz on this range. We'll try the next range, which should be 100 Hz to 3 kHz. Okay, so with both pots all the way down, that's over 140 Hz, and with the pots turned all the way up, we're up at over 4 kHz. So I mean, it can be made to work within the specified range, but it's not particularly controllable. What we'll do now is try moving the jumper to triangle wave, and doesn't look like a particularly good sine wave at this point, but let's try moving it to triangle, see what we get. And it doesn't look like a particularly good triangle wave, it still seems to be clipping, so we'll take it down some more and we'll turn the gain of that channel up on the scope. As we can see, it is DC coupled as well, so in fact I think one of the modifications that was suggested online was to put a capacitor in series with the output to make it AC coupled. The problem doing that, of course, is you'll reduce the operation at low frequency. It will give you a very distorted output. But you can see that it's given us quite a decent triangle wave at this setting, and at the moment we're at 1 volt per division on the scope, and the amplitude for that channel is just over 2 volts, about 2.5 volts. We'll go back to sine wave. It's looking like a better sine wave now. We'll turn the gain up a bit further again. Okay, what I'm going to do is I'm going to go to AC coupled. Okay, I've changed the triggering to channel 1. It wasn't particularly happy triggering on channel 2. We're getting these odd spikes at the peak of the sine wave, so I suspect that's possibly an artifact caused by the way that the IC generates a sine wave. And the next thing we'll do is try the next frequency range. So the next one should be 3 kHz to 65 kHz. Turn the pots right down again, and that is actually 3 kHz, so that's fairly close to what it's supposed to be. And the fine takes us up to 4.3 kHz, and if we increase the coarse all the way, that takes us up to 9 kHz. And if we turn them both all the way up, it takes us to 83 kHz. So I think the problem is the coarse and fine labelling is not very good, and they've got these in series, which is not really going to work very well with the values they've selected. However, the signal output is still reasonable, so we'll try the next frequency range, which is 65 kHz to 1 MHz. So with both pots all the way down, that's 52 kHz, which is fine. Fine takes us all the way to 74 kHz, and then with the course all the way up. That allows us to go all the way up to just over a megahertz. However, we have some significant distortion. Try changing the amplitude. So obviously something not working properly there at all. We'll try going to a triangle wave. And it actually looks very similar. Go back to a sine wave. Square wave is rounded off as well, so we do have a severe bandwidth limitation on the output for the square wave. We'll start turning the frequency down and see what the usable limit appears to be. I'd say it's about there, so it's about 100 kHz. It's probably as high as you can really go without getting bad distortion. I suspect this glitch at the top and bottom of each sine wave is an artifact caused by the IC, so it may well be that this is not a true IC. It could be a fake. I wouldn't expect to see something this severe. We're not at particularly high frequency yet. I've got no intention of going through and trying to remedy this. This is just how it comes out of the box. The sort of thing I would probably use this for is testing LCD monitors, that sort of thing. I've shown in the past how you can use function generators for testing monitors, and a simple circuit like this will be quite useful for that, where you don't want to tie up a bench signal generator, or maybe a couple of signal generators to generate the signals to drive the monitor. Using a few of these would be quite a nice solution. But in terms of whether this was worth what I paid for it, as I say, I paid about £4.50 delivered for it, and I think it is worth it. I think a bit of fun assembling it. It was fairly easy to put together, so nothing too exciting there. It's got a nice little enclosure which I'll put together in a few minutes. But as a starting point for doing some testing, learning about signal generators, that sort of thing, and then maybe using this as a means by which you can experiment to resolve the issues, I think this would be a very good learning tool. In fact, the fact it doesn't work is perhaps more beneficial to someone starting out, because it gives you something to work on, and trying to figure out what's causing the issues, getting the correct values for the pots and the various resistors might be quite a nice little project. So yes, I think this was worth the money. Not particularly exciting, but functional for what I paid, and may come in handy if I want to use it for some very basic testing. Okay, so that's the finished unit. As you can see, it does actually look quite nice when it's complete. Very cheap, barely functional. It does do the job up to a certain point, but certainly would need some work if you wanted to use it as a serious signal generator. But as a simple way to generate some basic signals, it would be quite useful. But in terms of the kit itself, yes, I think it's quite a nice little kit for a beginner. So I think a thumbs up for the £4.50 that I paid for it.